Hello, and welcome to Linear Algebra. This is lecture 24, and today's topic is the Cauchy-Schwarz inequality. Okay, so last time, we started talking about inner products and inner product spaces, which are vector spaces with inner products. This time, we're going to talk about some important inequalities that hold in every inner product space. Okay, so let's briefly recall the context we're in. So from now on, F is either R or C. V will be a vector space over F with an inner product. Right, so that's denoted with triangular brackets. Incidentally, from now on, I know that one of our notations for span is also triangular brackets. But now that we have triangular brackets for inner products, I will only ever write out the word span and not use triangular brackets for a span. So as to avoid confusion. Okay, so this will always denote an inner product. Well, so with an inner product. So that means that this is an element of the field, the scalar for all V and W in the vector space. Also recall the norm of a vector is defined to be the square root of the inner product of the vector with itself. And we say that two vectors are orthogonal if their inner product is equal to 0. Okay, the norm, also called the length, is greater than or equal to 0, and it's equal to 0 if and only if the vector is 0. Okay, the final thing I want to recall is from the end of class last time, a lemma we proved about projections. So given V and W in vector space, and let's go ahead and assume that W is not equal to 0 because that's the interesting case. We can find A in the field, U in the vector space with U orthogonal to W such that V is equal to A times W plus U. And we had an explicit formula for A. A is the inner product of V and W divided by the norm of W squared, or equivalently the inner product of V with W divided by the inner product of W with W. Right, and the picture is that you have V, have W, right? So then you have the line spanned by W, and this is A times W, this is U. And so you see that this A times W is the projection of the vector V onto the lines spanned by W. Right, so we have a nice explicit expression for the coefficient that you multiply W by to get the projection of V onto W. Okay, great. So now that we are all on the same page, let's go ahead and prove this inequality. So Cauchy-Schwarz. Also known as Cauchy-Schwarz, because Cauchy proved it for the standard inner product, and then Bunyarkovsky and Schwarz proved it for the integral inner product. But as we see now, it is true for any inner product on an inner product space. So here's what it says. And this is one of the most important inequalities in mathematics. This gets used all the time, everywhere. So if you have any two vectors, then for any vectors, we have that the modulus of the inner product, right? Inner product scalar, is bounded above by the size of V times the size of W, product of the norms. And equality holds if and only if V and W are collinear. Right, so one of them is a multiple of the other one. Okay. So let's prove this. Well, first, notice that this is easy if, say, W is the zero vector, since then both sides are equal to 0. Okay, so otherwise, let's assume that W is not equal to 0. And in that case, we can use the lemma from last time, and we can write V as 8 times W plus U with U orthogonal to W, and we have an explicit formula for A. So we can write V like this, and then use the Pythagorean theorem. Okay, so let's just start with the norm of V squared. The norm of V squared is equal to the norm of AW plus U squared. And by the Pythagorean theorem, that's the same as the norm of AW squared plus the norm of U squared. Right, because these two vectors are orthogonal to each other. And the first one, because the norm is positive homogeneous, I can write as mod A squared times the norm of W squared, and then I have the norm of U squared. Okay, now we have an explicit expression for A, so I can write that as that's the modulus of inner product of V with W divided by the inner product of norm W squared, all of that squared times the norm of W squared plus the norm of U squared. Okay, but now if we look here, we have a norm of W squared, and then it gets squared. So altogether on the bottom, I'm going to have norm of W to the fourth. And then here I have norm of W squared. So altogether, that gives me, well, on top, this inner product squared, on the bottom, the norm of W squared, and then plus norm of U squared. And the norm of U squared is greater than or equal to 0. So I can bound this below by just keeping this divided by norm of W squared. Okay, so notice I start with the norm of V squared, and I end up bounding that below by this quotient. So if I move this multiplying the opposite side, I end up with norm of V squared times norm of W squared is greater than or equal to the modulus of the inner product of V with W squared, right? And that's exactly what I wanted to show by taking square roots of both sides. And it's okay to take square root of both sides of the inequality, because they are non-negative numbers that are being squared. So then the square root will preserve the inequality. Right? And also this proof tells us exactly when we have equality. Right? Moreover, right? Because the only place where I failed to have an equal sign was here. And that inequality came about because I dropped this mod u squared. Right? So we would continue to have an equal sign if I didn't have u. Right? So we get equality precisely when the norm of u squared is equal to 0. Which is when u is equal to 0, or v is equal to a times w. Right? So equality holds precisely when they are collinear. One of them is a multiple of the other one. Okay, wonderful. So that's the Cauchy-Schwarz inequality. And notice the proof was actually pretty simple because I had this lemma from last time about how to project one vector onto another one. And this works in any inner product space. So in a moment, I'll start writing down some particular cases, and you'll see that we proved some inequalities that look really complicated, but because they're pretty simple if you write them in the most general setting, in this abstract setting of an arbitrary inner product space, the proof becomes pretty simple. That's something that happens a lot in mathematics. Like if you write something in the most abstract setting where it's true, of course, it can be hard to figure out what that setting is. But if you find that setting, then the proof is usually pretty simple because you've abstracted away everything except what you need for the proof. So here is a corollary, really, but it's so important that we'll call it a theorem. This is known as the triangle inequality. So this says that for any v and w in the vector space, the length of v plus w is bounded above by the length of v plus the length of w. With equality, if and only if v is equal to lambda w with lambda non-negative. Right. So last time for the Cauchy-Schwarz inequality, we get equality when v is equal to a times w, any a. This case, we get equality if v is equal to lambda w, but lambda needs to be a non-negative scalar, right? So they have to be collinear, they have to be on the same line, and they have to be pointing in the same direction. Okay, so why is it called the triangle inequality? Well, as before, imagine that you have vectors v and w. Now, you use those, so you translate the w to the other end, and then you use them to find v plus w, right? So, okay, there's the triangle. So what the triangle inequality is telling you is that if you want to go from this point to this point, then going directly there is going to be shorter than if you go along v and then along w, right? So it says that the one side of a triangle, it cannot be longer than the sum of the other two sides of the triangle. And the equality case, so you can see it clearly if you think about it geometrically, the equality when is going from here to here going to be just as good as going from here to here and then from here to here? Well, when this guy was on your way, right? So you get equality precisely when this midpoint is already on this line. And that's exactly when the two vectors were pointing in the same direction. Okay, so that's the picture. The proof, you'll see, follows immediately from Cauchy-Schwarz. So let's prove this. Okay, so let's start with the left-hand side squared, just to avoid writing a lot of square roots. So let's start with the squared. By definition, this is equal to the inner product of v plus w with itself. And because the inner product is linear in the first entry, I can write this as v inner product with v plus w inner product with v plus w. Now the inner product is actually, it's additive in both entries. So now I can expand that out into inner product of v with v and inner product with v with w. And then over here, same thing, but now starting with w, v, and then w with w. Okay, and now here we're going to recognize I have v with w, and then here I have them in the opposite order. So I can flip the order, but I pay for it with a complex conjugate. Okay, so now inner product v with v, I'm going to go ahead and write that as the norm of v squared. Then here I have a complex number plus that same number but conjugate, right? Well, if you have a complex number plus its conjugate, the imaginary parts cancel out and the real parts get added together. So I end up with 2 times the real part of the inner product of v with w, and then this norm of w squared. Okay, so the real part of a complex number is less than or equal to the modulus of that complex number. Right, so if the complex number is a plus ib, then here I have real part, that's just a, and here I have modulus, that would be the square root of a squared plus b squared. Right, so if b were 0, then a would be less than or equal to the square root of a squared. And adding the b just makes it no smaller. So I have this inequality. Okay, but now I use Cauchy-Schwarz and I write this as less than or equal to 2 times the norm of v times the norm of w, and then plus the norm of w squared. Okay, and this we recognize as the norm of v plus the norm of w, all that's squared. Okay, and then taking square roots of both sides would give us the triangle inequality, right? And again, it's okay to take square roots of both sides of this inequality because both of the numbers that we're squaring are positive, or at least non-negative. Right? So norm of v plus w is less than or equal to the norm of v plus the norm of w. Okay, so now what about if we have equality? If we have equality and let's say that w is not equal to 0, right? If w is equal to 0, then of course you have equality trivially because both sides are just the norm of v. Then, okay, well, we used 2 inequalities here. So if this is equal to this, then both of these are actually equalities, right? So if you have equality here, then you know from the previous theorem that you must have the V is equal to a multiple of W. So V is equal to, say, lambda W for some lambda, right? So that's gives us equality here. And then we still have equality here. So what does that tell us? And the real part of inner product of V with W has to be equal to the modulus of the inner product of V with W. Now here, this, if V is equal to lambda W, this is equal to lambda times, real part of lambda times the inner product of W with W. And this, if V is equal to lambda W, would be modulus of lambda times the modulus of the inner product of W with W. Okay. Now, since the inner product of W with W is a positive real number, right? W is not zero, it's a strictly positive real number. Then I could cancel it out from both sides of this equality. The real part of lambda is equal to the modulus of lambda, right? But the modulus of lambda is equal to, the square root of the real part of lambda squared plus the imaginary part of lambda squared. And if you leave this term out, you get the absolute value of the real part. So the only way that the real part is equal to this is if lambda is already real, and then it's non-negative. Right? And that's what we wanted to show. Okay, here is a simple corollary. For any UVW in V, the norm of U minus V is less than or equal to the norm of U minus W plus the norm of W minus V. So it's an immediate corollary because here we said that for any vectors, the norm of this vector plus the norm of this vector is bounded below by the norm of their sum, right? So over here, if you just apply that to this vector and this vector, it says that the norm of this vector plus the norm of this vector is bounded below by the norm of their sum, and this guy plus this guy is this guy. So it's an immediate corollary. Why is it nice to write it like this? Well, so again, in terms of triangles, you have this picture. So U minus W here, say, W minus V here, say, and then this would be U minus V. But you can think of this as being the vector that goes from V to U, right? So if this point is V, this point is U, this vector is the vector that goes from V to U. This vector correspondingly, oh, sorry, I wrote that wrong. This, I would have U here and V here and W here. So you can think of the length of this vector as being the distance between U and V. And same thing here, this is the distance between U and W. And the length of this would be the distance between W and V. So you can rewrite this as saying the distance between U and V is less than or equal to the distance between U and W plus the distance between W and V. And like we were saying a moment ago, this means that what you're saying is if you're going to go from U to V, then it can only make it longer if you have to stop at W on your way, right? It can't make it shorter. Okay, so let's look at some examples. What does this say for the standard inner product? So on Cn or on Rn, if you're just using real numbers. Okay, so Cauchy-Schwarz, right? So this says that the inner product of V and W is bounded above by the norm of V times the norm of W. So this looks like this. The sum J goes from 1 to N of Vj Wj bar is less than or equal to the square root sum J goes from 1 to N of mod Vj squared times the square root sum J goes from 1 to N of modulus Wj squared. Okay, and this is true for any n numbers, complex numbers v1 through vn, and n complex numbers w1 through wn. Correspondingly, the triangle inequality, right, which says that the norm of v plus w is bounded above by the norm of v plus the norm of w. So in case of the standard inner product, this says the square root of the sum of absolute value wj plus vj plus wj modulus squared, j goes from 1 to n, square root is bounded above by the square root, sum j goes from 1 to n, modulus vj squared, plus the square root, sum j goes from 1 to n, modulus wj squared. Okay. Right. So alternately, let's say you want to use matrix product notation, then Cauchy-Schwarz would have the form, the inner product I can write, so this would be the modulus of W star V, and this will be bounded above by the, so let's put a square here, and then it'll be bounded above by V star V, W star W, right? So this is a scalar and this is a scalar, so this is just a scalar at the end. Okay, let's do another example. Or let's do the same example, sort of, in a different way. Let's say we identify the m by n matrices with C of dimension m times n. Then the standard inner product becomes, so I start with two matrices, and then their inner product will be the sum j goes from 1 to n, so, or let's do j goes from 1 to m, k goes from 1 to n, and then you would have a j k, b j k bar, right? So what I mean by identify this is we're just gonna, if you think of a matrix, instead of being a rectangle, just put those entries into a column. Then you end up with a column in here, right? And we have a standard inner product here, so you could apply that to these columns you got from the matrices to get a number. And so altogether, you're going from this inner product of these two matrices, and you're just taking all of the corresponding entries, multiplying them against the other, and putting a bar. Now, recall that B star has kj entry given by bjk bar, right? So remember that the way we form the adjoint matrix is we change the order here, so we're doing the transpose, and then we put a complex conjugate. So I can rewrite this inner product as the sum j goes from 1 to m, sum k goes from 1 to n of the jkth entry of A times the kj entry of B star, and that's the same as the sum j goes from 1 to n of A B star, and we're taking the jj entry, and so that's equal to the trace of A B star. And because the trace has this nice property we talked about, that's also equal to the trace of B star A. Okay, so this gets a name. This is the Frobenius inner product. And the Frobenius norm of a matrix is equal to the square root of the trace of A star A. Well, sorry, it yeah, A star A. So here, Cauchy-Schwarz takes the form. So it says that the trace of A B star or B star A modulus squared is less than or equal to the trace of A star times the trace of B star. Right? And if you look at it like this, it might seem a little strange in that, you know, how in the world are you going to prove this fact about traces of matrices? But it's just a particular case of Cauchy-Schwarz, which we've now proven in arbitrary inner product spaces. Here's another example to show, you know, that this one proof gives us a lot of very different looking particular cases, even on Rn, say. Let's pick some numbers. Let C1 through Cn be positive numbers. We get an inner product on Rn by setting the inner product of x and y, these are vectors x and y, to be the sum j goes from 1 to n, cj times xj, yj. Right? So if all of the cj's were equal to 1, we would get the standard dot product. Right? But they don't have to be equal to 1. They can be any positive numbers, and I will still get an inner product. If we use this inner product, the standard basis vectors will still be orthogonal, but they will no longer be unit vectors. They will no longer have length 1. Right? Unless all of the CJs are equal to 1. right? In fact, the norm of EJ, well, that by definition is the square root of the inner product of EJ with itself. So that would be the inner product of CJ. Sorry, not the inner product, the square root of CJ. If n is equal to 2, the unit vectors are given by, so let's draw some cases. So if C1 is equal to C2 is equal to 1, then we just have the usual inner product, and so the unit vector is just the ball of radius 1. So the sphere of radius 1, in this case, just the unit circle. But for example, we can easily arrange for the unit vectors to make up an ellipse. Say this one is what would happen if C1 were equal to 1/4 and C2 were equal to 1, then the unit vectors would make up that ellipse. And you could rotate that 90 degrees. And this is what the unit vectors would look like if C1 is equal to 1 and C2 is equal to 1/4. But no matter what CJs you pick, as long as they're all positive, you get an inner product. And since we've proven Cauchy-Schwarz and triangle inequality for every inner product, those are true. So for example, the Cauchy-Schwarz inequality here takes this form. It says that for any numbers, positive numbers, CJ, and arbitrary numbers, XJ, YJ, the absolute value of this sum is bounded above by the sum of CJ, XJ squared. J goes from 1 to n. And J goes from 1 to n of CJ, YJ squared. Okay? Similarly, so you can think of this as being a weighted version of the standard inner product. You can also do a weighted version of the standard inner product we did involving an integral. So let's say that H goes from 0, 1 to the real numbers. You get is a continuous positive function. We get an inner product on the continuous complex valued functions on 0, 1. By saying that the inner product of two functions, f and g, is going to be the integral from 0 of 1 of h of x times f of x, g of x bar dx. So same thing I had before, but now I put a weight, this h. And so here, Cauchy-Schwarz, right, which we've already proven in all inner product spaces. So because this gives you an inner product, you have the Cauchy-Schwarz inequality. And it says, in this case, that the integral of h of x, f of x, g of x, say squared, is bounded above by the product integral from 0 to 1 of h of x mod f of x squared dx times the integral from 0 to 1 of h of x mod g of x squared dx. Right, so there you go, another particular case. Okay, let's do one more. Another infinite dimensional one. So let's let little l2 denote the square summable sequences over the real numbers. So what does that mean? So an element in little l2 is a sequence. And so A would be A1, A2, and so on, such that the square summable business, that's saying that the sum j goes from 1 to infinity of aj squared is finite, right? So this series converges. And then we're going to define the inner product of A and B to be the sum j goes from 1 to infinity of aj bj. So first thing we should worry about is, does this make sense? Does this series converge? So let's reassure ourselves. Let's check that this makes sense, i.e., that the series converges. Okay, so how do we know the series converges? Well, for any natural number, take the sum j goes from 1 to n of aj, bj. Let's say you put absolute values inside. Okay, so now using Cauchy-Schwarz inequality for Rn, we can bound that by the square root of the sum of the aj squared, j goes from 1 to n, times the square root of the sum j goes from 1 to n of bj squared. And then I can definitely bound that by the sum j goes from 1 to n, j goes from 1 to infinity of aj squared, right? Because all of the terms that I'm adding, here that I didn't have here are still sums of squares, so they are non-negative. So only making it bigger. And this we know is finite because the sequences AJs and BJs are square summable. So this is now a fixed real number, independent of n. So for any n, this series is bounded above by this fixed real number. Since this series on the left is made up of non-negative terms, the fact that it is bounded, the fact that the partial sums are bounded implies that it converges. Right, so if you're adding non-negative numbers, the sum is only getting bigger and bigger and bigger, right? But if you know there's some bound, some real number that it doesn't get beyond, then it has to converge to something less than or equal to that. So hence the series. Sum j goes from 1 to n, to infinity of aj bj converges. In fact, it converges absolutely, right? So remember, that just means that it converges even after you put absolute values of the individual terms. Okay, and then, and we get Cauchy-Schwarz. We get that the modulus of this is bounded above by this number. Right, and let me just mention that we could also have worked with little L2 with complex entries. So these would be sequences A1, A2, and so on with AJ complex numbers for all j, such that the sum j goes from 1 to infinity of the modulus of aj squared is finite. And defined an inner product of A and B to be the infinite sum AJ BJ bar. We could also include a weight. So if C is C1, C2, and so on is a sequence of positive numbers, no convergence requirement, just a sequence of positive numbers, then the inner product of two sequences A, B, you can find to be sum j goes from 1 to infinity of Cj, and then take AJ, Bj bar. This is inner product. Okay, and my point again is that we've proven these two inequalities, Cauchy-Schwarz and triangle, on an arbitrary inner product spaces. And then it turns out that there are tons of different inner product spaces, and we've proven these inequalities in each of them, which did it all in one go. Okay, and we'll stop there for today, pick it up from there next time.